doping. Doped semiconductor is extrinsic semiconductor. On doping with a trivalent atom, the four-fold coordination is no longer satisfied and a hole is formed. Okay, on account of missing bond. This is known as p-type semiconductor, and there are excess of holes. A pentavalent dopant atom is added to the pure semiconductor. Then what will happen? Pentavalent, right? 5 valency electrons. So what will happen if it pairs up with other 4 valent atom like silicon or germanium? 1 electron will be excess. Okay, 1 electron will be excess. Then what will happen? There are excess number of electrons. This type of semiconductor is known as N-type semiconductors. If majority charge carriers are holes, then it is called P-type semiconductor. If majority charge carriers are electrons, then it is called N-type semiconductor. Thus, in an extrinsic semiconductor, the electron concentration is not equal to the hole concentration. Okay, that is the electron and hole concentrations are given by Ne into NH is equal to Ni square. Okay, what is Ni? This is the concentration in intrinsic semiconductor at the same temperature. Like whereas in case of impure semiconductor. Okay, so extrinsic semiconductors, you can see here how actually we wrote valency band and then conduction band. The effect of dopants is to introduce additional energy levels in the band gap. When pentavalent and trivalent dopants are introduced, additional energy levels called the donor levels and the acceptor levels are created in the forbidden energy gap. The Fermi level for N-type is closer to the conduction band, while for the P-type it is closer to the valency band. We'll come to this topic, direct and indirect band gap semiconductors. In a direct band gap semiconductor, the minimum of the valency band and the maximum of the conduction band occur at the same value of K. Okay, here you can see same value of K, minimum of the valency band and maximum of the conduction band occur at the same value of K. See, you can see they are happening at the same position. Consequently, in a direct band gap semiconductors, when electrons and holes recombine, all the energy is radiated in the form of a photon. Okay, when electron and hole they recombine, what will happen? The energy is emitted out in the form of photon. The emission wavelength of the common semiconductors, which are used for making LEDs and lasers, are given in that. Okay, you can understand LEDs and lasers. What wavelength actually we are getting in case of lasers and all we have studied actually. What will happen when photon is emitted out? If it falls within the range of, visible range, we call it as, which colored laser it is, like helium neon, red color laser, something like that. Semiconductor laser gives out, infrared laser, all these types. So in the emission wavelength of the common semiconductor, which are used for LEDs and lasers are, earlier we have discussed. In an indirect band gap semiconductor, the minimum of the conduction band. In an indirect band gap semiconductor, the minimum of the conduction band and the maximum of the valency band do not occur at the same value of K. See, you can see the minimum of this band, the maximum of this band it is not occurring at the same value of K. So hence, whenever electron hole pairs are formed or recombined, there is a change in the momentum. Okay, this momentum is given to the lattice atoms. Thus, electron-hole combination in an indirect band gap semiconductor gives rise to non-radiative transition that leads to heating of the lattice. So it will get heated up because the minimum of the conduction band and the maximum of the valency band, they are not occurring at the same value of K. That is why when hole and electron, when they recombine, okay, non-radiative transition takes place, and because that leads to heating of the lattice. Okay, law of mass action, what it says? Okay, let Ne and NH be the electron and hole concentration in an extrinsic semiconductor at any temperature T. Okay, then let Ni be the electron hole concentration in the intrinsic semiconductor at the same temperature. Then the relation Ni square is equal to Ne into Nh, hole concentration and electron concentration Ni. This is known as law of mass action. This enables to know the carrier concentration of one carrier type. If you know one carrier concentration, then you can find out another carrier concentration by using this law of mass action. This actually resembles the law which occurs in the equilibrium of chemical reactions in physical chemistry. There also use same thing. Ni square is equal to Ne into Nh. What are free charge carriers? They are actually carriers that exist in a semiconductor at a temperature above 0 Kelvin. Electrons in the conduction band and the holes in the valency band. Okay. So an empty electron state is called a hole. So whenever an electron jumps from valency band to conduction band, wherever electron left that place, that is considered as a hole. Okay. An empty electron state, that is why it is called as hole. Electrical properties of solid substances depends on the momentum, energy, spin, and magnetic moment of electrons in it. Okay, these many things will affect the electrical properties of any substance, any material. N-type semiconductors are actually electrons. Here, electrons are majority charge carriers. P-type majority charge carriers are holes. Okay, how do we get P-type and then N-type? If you add a third group element to fourth group element, or silicon or germanium, then you get P-type semiconductor. If you add fifth group element to the silicon or germanium, then you get N-type semiconductors. Thus, the carrier concentration can be equal or unequal. If unequal, it is extrinsic. If N0 is equal to B0, and B0 means it is hole concentration. N0 means electron concentration. If both are equal, then the concentration becomes equal to the intrinsic concentration. All the atoms of semiconductor at 0 Kelvin are electrically neutral atoms. See, remember, all the atoms in a semiconductor at 0 Kelvin are electrically neutral atoms. Okay, electrons and holes are mobile charges. Intrinsic semiconductor, under an externally applied field, the electrons which are excited into conduction band by thermal means okay, at the same time, the holes in the valency band also move, but in a direction opposite to that of electrons. Okay, if electrons move in one particular direction, holes will move in opposite direction. The conductivity of the intrinsic semiconductor depends on the concentration of these charge carriers, Ne and Nh. We can define the mobility of conduction electrons and holes, mu E, and mobility mu here. It is represented by mu. Mu E and mu H as the drift velocity acquired by them under unit field gradient. Okay, then mobility is equal to drift velocity by field gradient. Okay, meter per second per volts per meter. We can write the conductivity of semiconductor as sigma is equal to Ne E mu E plus Nh E mu H. We will be deriving it soon. E electric charge, Ne and Nh concentration per unit volume of electron and hole respectively. Extrinsic semiconductors are, in extrinsic semiconductors, the conduction is due to presence of deliberate addition of controlled quantities of impurities to a pure semiconductor is called doping. I already told you, we add certain materials like third group or fifth group elements to silicon and germanium in order to get extrinsic semiconductors. In these semiconductors, current is transported in them through two different processes, namely diffusion and drift. So, J is current density, sigma is conductivity, okay. Mu is mobility of charge carriers. Mu E means mobility of charge carrier electron, mobility of mu H means mobility of charge carrier hole. Drift and diffusion, I told you, current is transported in semiconductors mainly because of these two processes. They are called drift and diffusion. What is drift? Under the influence of an external electric field, the charge carriers are forced to move in one particular direction. okay, constituting electric current. This phenomena is known as drift. Because of the external field applied, electric field applied, the charge carriers, that means electrons and holes, they are forced to move in one particular direction. Okay, that is called drift. Okay, let there be n electrons in a semiconductor. The electric field is E. They are drifted with a drift velocity Vd. Okay, you can see this is semiconductor and electric field is applied in x direction. So this is connected to some power supply. Drift charge carriers in a semiconductor, they are shown like this. Holes are here, electrons are here. I already told you, if electron is moving in one direction means holes will be moving in opposite direction. Then the current density J is equal to NEVD. Then conductivity sigma is equal to J by E. That is equal to NEVD by A. The drift velocity is also given by Vd, which is equal to V suffix D. That is equal to mu NE. Okay. Where mu n is mobility of electrons. Vd is drift velocity. E is field that you have applied. So J is equal to, current density J is equal to NE mu NE, because J is equal to NE Vd. Vd means mu NE. So NE mu NE is for electrons. Current density. Sigma is equal to J by E. This equation becomes J by E. What is J? NE mu NE by E, sigma. Then NE mu N you get for sigma, because it is J by E. Rho is equal to 1 by sigma. Resistivity is equal to 1 by conductivity. That is equal to 1 by NE mu N. In the case of a semiconductor, the drift current density due to electrons is given by Jn drift is equal to Ne mu Ne. Okay. For holes, same formula. You write wherever N is there, you write P. P represents holes here. J suffix P, drift current density because of drift is equal to P mu P E. P mu P E. Then total convex density is because of electrons and holes. Then J drift is equal to Jn drift plus Jp drift. Then N mu N E plus P mu P E, total current density. Okay, because of drift. Then EE is a common term here. You take out EE into N mu N plus P mu P. Then sigma drift is equal to J by E. This entire equation divided by E. Then what you get? En mu N plus EP mu P. For intrinsic semiconductor, okay, N is equal to Q. Number of electrons is equal to number of holes. That is equal to Ni. Then sigma I drift. Okay. Sigma I drift is equal to NIE into mu N plus mu P. Okay. Here N is equal to P. You write instead of N and P, you write N suffix I. Then Ni here. Then Ni is a common term. Mu N plus mu P. Sigma I drift is equal to Ni E into mu N plus mu P.